Hi, I'm Sherman. Today I will give you a short tutorial on how to use an atomic force microscope. This is the table of contents. It shows the flow of this video presentation. Firstly, I will start off with the aim of this tutorial. Basically, using the tapping mode of AFM, I will demonstrate how to obtain AFM images. Right now, let us proceed to the working principles of an AFM. In the AFM, it relies on the interaction forces between the scanning probe and sample surface. The scanning probe is a tip attached to the end of a cantilever. This cantilever is attached to a piezoelectric scanner which is able to move the cantilever in the X, Y, and Z directions. As the tip scans the sample surface, the laser beam is incident on the back of the cantilever where the tip is attached. The laser beam is deflected to a position-sensitive photodetector. Since the interaction forces are dependent on the tip and sample surface, the different contours on the sample surface results in changes in the interaction force. This causes the position of the laser beam on the photodetector to shift and registers a voltage difference which is then sent to the feedback loop. The piezoelectric scanner will then adjust the position of the cantilever accordingly so as to maintain a constant interaction force between the tip and sample surface. This data is then sent to a computer software where the scan image can be observed. This is how a piezoelectric scanner looks like. And this is how a scanning probe looks like imaged by an SEM. Next, I will move on to touch on the forces of interaction between the tip and sample. The dominant type of force interaction between the tip and sample is dependent on the vertical distance between them. The potential energy of this interaction can be described by the Lennard-Jones potential as shown in equation 1. Over here, Z refers to the distance between the tip and sample surface. 1 over Z to the power of 12 describes the repulsion due to the Pauli exclusion principle. And the 1 over Z to the power of 6 term describes the attraction due to van der Waals forces. The force interaction can be found by taking the negative derivative of the potential energy shown in equation 2. The interaction force against Z is being shown in figure 4. In tapping mode, the overall interaction force is attractive in nature, and is due to the fluid surface tension forces as well as the van der Waals forces. This regime is denoted by the blue highlighted lines. So now, I will discuss about the tapping mode. In tapping mode, the end of the tip cantilever is set into oscillation at or slightly lesser than its resonant frequency. The amplitude of oscillation typically ranges from 20 nanometers to 100 nanometers and occurs in the attractive regime of the Lennard-Jones potential. As the cantilever oscillates, at the point of oscillation where the tip is closest to the sample surface, the tip experiences an attractive force which dampens the oscillation. This results in a reduction in the amplitude of the cantilever. To map the surface topography of the sample, constant oscillation amplitude is maintained. This constant amplitude is called set point amplitude. Hence, the vertical position of the scanner at each XY data point in order to maintain a constant set point amplitude is stored in the software to form the topography of the sample surface. So now, let us proceed to the experimental procedures. To begin an AFM scan, the tapping mode probe is loaded onto the scanner and the sample is loaded onto the scanning stage. The stage vacuum is turned on so as to secure the sample. Using the computer softwares like Nanoscope, the laser is then aligned to the tip using the screws. The tip, followed by the surface and optics, are then focused. The tip is then engaged after setting the initial parameters of the scan. The parameters are then optimized to get a good image. Next, we will move on to the result section. Figure 4 shows the AFM image of a silicon dioxide test sample with protruding circular patterns, while in Figure 5 shows that of a depressed square pattern. Using the section analysis function, we can calibrate the AFM scanner and electronics with the known pitch cluster features of the test samples. Next, let us move on to the discussion section. First, I will talk about bowing effects. Measurements of the depth, width, pitch, and diameter of the circular and square features can be analyzed after applying a second-order flattening function to remove the bowing effects. Bowing effects are caused by the piezoelectric scanner as they normally move in a curved motion over a sample surface. Next, I will move on to the typical sources of errors in AFM. Possible sources of errors include asymmetric tip geometry and floor and acoustic vibrations. Asymmetric geometry of the tip results in varied scan profiles at different scan angles, as shown in the figure. Also, for the floor of a building, it can oscillate several micrometers at frequencies below 5 Hz. If these vibrations are not filtered, it can cause a periodic modulation in the AFM image. Such vibrations can be started by people opening or closing the doors. Acoustic vibrations from a person's voice can also cause artifacts in an AFM image. To minimize such errors while performing a scan, it is advisable to close the AFM hood and use a damping table. Tripping effect occurs when a set voltage is applied to the piezo scanner to move the scan head to a certain direction. The piezo tends to continue to move in the same direction for a certain period of time even after scanning has started. Lastly, amplitude set point and scan rate affects the image quality as well. For a higher amplitude set point, the tip and sample surface distance is larger, leading to poorer tracking of the surface. As the scan rate increases, the time spent by the tip at each scan line is less. This will lead to a poorer image quality, as a finite amount of time is needed to establish a full force interaction. This is the end of the tutorial. For any queries, you can reach me through email at shermantan@u.nus.edu.